So let's take a look at electrostatic potential. In electrostatics, one of the most important functions is the potential. We start with looking back at our potential energy relations, and we're going to take the one where we had a bunch of point charges and we're interested in the potential energy of some test charge Q0, and we'll say that it's at the point A. Potential energy of this test charge in the neighborhood of these Q sub i's was given by this expression here, and we derived this. You'll see that it has a Q0 in it, so in order to get a potential energy, you have to have the Q0, which is the potential energy of Q0 due to the other Q's. The r sub i's are the scalar distances between Q0 and each Q sub I, as we've shown up here. If you look at this equation here, Q0 is in all of them, and so we could bring that outside of this sum. So let's do that. We'll pull the Q0 out. We have a Q0 times this quantity right here, and so what we're interested in is some kind of parameter which is independent of the test charge. Here's our repeated equation here. So what we're going to do is define the potential of a given point charge array so that these are all the Q sub i's at the point A. And that's going to be the potential at the point A of Q0 divided by Q0. So that way we get rid of the Q0 dependence. You might think of this potential as being this potential energy of a point charge that was a unit charge in magnitude. We take this Q0 away because we've divided by it. We're left with this expression right here. So we've divided the U by the Q0 to get this expression. This equation has the convention that potential is 0 at an infinite distance because all these r sub i's would go to infinity. So what that means then is if you had all the charges like this and the point where you're trying to find the potential, this point A, was at infinity, then all of the r sub i's would be infinitely long, so therefore this thing would go to 0. The other thing to note is that the potential energy and the potential are both scalars. There's no vector quantity here. This is a distance, this is a charge, this is k, so all of this ends up being a scalar, and of course the sum of scalars is equal to a scalar. If we take a look at this electric potential at the point r, so it's v of the vector r at a given point, defined of course by the vector r. In magnitude, this potential is equal to the electrostatic potential energy that a positive unit charge would have if it were placed at the point r. And remember, we just divided by Q0, and so that would mean it would be like a unit charge in terms of potential energy. This quantity V, the potential, has the units of potential energy divided by charge, and so that would be energy over charge, and you're well aware that that would be joules per coulomb, and we define a single joule per coulomb as a volt. So if we have Q sub I of either sign, and it could even be a mix, if we take the electric field and look at the way the potential changes when we go in different directions, the potential increases if you move in the direction which is opposite to the electric field. And of course the inverse. The potential decreases if you move in the same direction as the electric field. One way to remember this is that if you are opposing the electric field with a test charge that of course is positive, you have to push. And so you're doing work, and since energy is conserved, that goes into the potential energy. Potential energy has to increase when you are doing work, and when you're doing work, you're moving opposite to the electric field. Of course, the inverse is that if you move in the same direction as the E field, that would be like sliding down the hill. You lose potential energy, and so on. So you get a free ride, so to speak, because you're up here, but you'll lose potential energy. Over here, you're going up the hill. The potential energy increases. In terms of electric fields, if you have some streamlines where the E field is in this direction here, okay, so if you go this direction, you're going from lower to higher. If you go in this direction, you're going from higher to lower in terms of potential. The same thing goes for just a uniform electric field. So for example, if you have these plus and minus charge sheets, you remember the E field is uniform in here, and it goes from the plus charge sheet to the minus charge sheet. And so I've shown these as these arrows here. Well, if you were to do the same kind of argument, if you go in this direction, so you go from minus to plus, with a plus charge you're pushing. You have to push to get from here to here. So you have higher potential over here. Vice versa, if you go from here along the E fields, you're going higher, lower. If you want to think in terms of the polarity of this system here, if you're going from minus to plus, you're going from lower to higher potential. When these become conductors and you're putting a battery across here, if you want the potential to be lower here and higher here, you put the minus terminal of the battery here and the plus terminal of the battery here. And of course the E field will be like you see here. We derive for a test charge the potential energy in terms of work. And so that's where we want to get the electric potential, the potential energy, and the work tied together. Here's the change in potential energy. This is an equation which we worked on before. If we're going from A to B, then the potential energy at B minus the potential energy of A is given by this integral. This integral right here is the work done by the electric force on Q0 due to the E field. If you recall, if you put a minus sign here, you're getting the work done by some external agent in moving from A to B. So it's a plus sign here. So look at it this way, that if you are doing work, then that will be equal to minus this integral right here. We want to think of this work here because that's always going to tell you whether or not the potential is going up or down, which tells you is this a plus quantity or a minus quantity here. So that's why we want to connect this integral here with the work done, and that's why there's a minus sign here. Well, if you divide by Q0, so you take all of these terms here and divide by Q0, you get this mess. So we have here the change in the U divided by Q0. We have each potential energy divided by Q0. We have the term for the work done, and then we decide which is plus and which is minus. If it's the work done by the force, it's minus. If it's the work done by us, it's a plus. All that means is that you take this term here and you use a minus sign here, and that'll give you the work done by the external agent. Then the change in voltage is equal to the voltage at B minus the voltage at A. And notice I use the word voltage. I really mean potential, but they're equivalent. The potential difference then here will be given by the work that we calculate in terms of the E field now. So this would be per unit charge. So in other words, we divide by Q0. This quotient here is in fact the E field because the force on Q0 is equal to Q0 times E. So if we just look at the straight relationship between the change in potential between the 2 points, it's equal to the integral of the E field dot dl from A to B. This is a fundamental equation that relates potential and the E field. This delta V then gives the work done by an external agent, that's you, me, or us, to move a unit charge from A to B. Simply what we're doing here is that if we divide by Q0, that's the same thing as a unit charge operating here. So here's some factoids. One is the difference in potential. This delta V is really the only measurable quantity. If you were to measure, for example, on a wire the potential difference between 2 points, you'd put a probe at that point B and you put a probe at point A, and your meter would give you the difference. So we always have to have 2 points to measure a potential, and sometimes you've probably heard potential difference. That's where these kinds of terms evolve. You can add or subtract any constant value to V. This does not affect delta V. So think of it this way. If I added to V sub B some V0, and I added an additional potential to V sub A, the minus sign would cancel the V0. So to be plus V0 minus V0, you end up with the same difference. And because that's the fundamental quantity, it really doesn't matter if you add a constant or not. There are a few exceptions to the following. We usually take V equal to 0 at infinity. There's some cases where you get into trouble when you do that, and we'll talk about those. V sub r then is equivalent to the work done by you, me, or we to bring a unit charge from infinity to the point given by the vector r. Let's suppose we have a point charge Q at the origin right here, and we're interested in the electric potential at a point P. So we'll define that in terms of the position vector R. Okay, so this is somewhat repetitive because we talked about potential energy in these terms. Let's continue here. We want the potential at this point right here defined by the vector R. We know that if we start at infinity and we take a Q0 and move it from Q0 towards the point P right here, we can take the position of Q0 and define it in terms of this R prime and move that R prime from Q0 at infinity to the point P. If we look at the equations, then the E field at the point R prime, so that's this right here, is equal to this quantity right here. It's kq over r prime squared r hat prime. Okay, so remember, this is the origin of the charge. That's q. The vector between here and this point right here we'll take as r prime. The direction of the field right here would be in the same direction as r prime. So you might consider this as r prime hat. So the work done from getting from here along this path here, call it C, is equal to what we had before. This is the force right here. This is the force on Q0. So this is the Coulomb force really. We take the direction of that force and dot it into the dl prime, which are these little vectors that are along the path. Let's start again. The first thing I want to show is that if we reverse the path, so if we go in this direction right here, all we do is change the sign of the integral. I'm still calculating the work from infinity to r, but I'm switching the path, I'm going to just call it C prime, from the point in question to infinity. So that's why we changed the sign to plus. But the answer is still the work going from infinity to r. These are arbitrary paths, and so in order to make this integral easier, I'm going to take the path from the position r to infinity to be just along the same direction as r. From here to infinity we're going to stay in the same direction. What we're doing is we're taking this Q0, starting here and moving it along this straight line to infinity. And this big long vector is r prime as we move from here, say, to this point here. dl prime is in the same direction as dr, r hat, so we can rewrite the work that we're going to be doing as a plus sign here, and it's kqqq0 over r squared, where now r is the distance from q to the point that we're moving. And that'll be in the r hat direction, and dl is a little differential of length along that path. So if we repeat then, this is the equation that we just had. Here's the work done that we're going to calculate, and here's the path. So we're going to go from this direction to here, and we're using the entire vector r prime to be equal to the vector r for the point as we move it along here. So if we switch our dl to our dr r prime, we have 1 over r squared, that's this r squared here. We've removed kqqq0 from the integral here, and r hat dot r hat will give us unity, so we're left then with a simple integral over dr. And here's our prefactor here. Doing the integral, we get minus 1 over r evaluated at these two positions. And remember, because we're going from r to infinity, the infinity is at the top and the little r is at the bottom. So taking that integral then, the work which would have been from infinity to r, but because we switch the sign, we get a plus sign here, which is what we should. So let me explain that. The reason that's plus is that our test charge is positive. Our charge at the origin is positive. So as we push in this direction, we should be raising the potential energy, and so therefore this point here should be plus compared to infinity. So that's why this is a plus. How we did the calculation is we reversed it, but we changed the sign. We changed that to a plus sign, just because it was easier to see. So here's our potential then. This is the work done to go from infinity to the position r, divided by Q0. We get rid of Q0, and so we have a term which is only proportional to the charge at the origin and the distance from the origin. Okay, so this holds for r in any direction from the origin. So we usually just write this without any vector here because it's only dependent on the position. This is something I don't want you to forget. This equation here, which holds for a point charge, is very useful. So let's look at the electric potential of a charge distribution, and we'll consider a volume charge density rho of our r prime. This is the source point, and we're interested in V at a field point r. Let's limit our interest where we have rho of r prime that's contained. So that just means that it doesn't extend to infinity. Turns out that's not important, but we'll do that anyway. And we'll take the case where r is either inside or outside of this charge distribution. So let's pretend that r is outside. Here's what I'm talking about. We have this volume, let's call it tau prime. It has the rho of r prime in this volume here. And we have a field point right here. So that's what r defines. Here's our origin. So this is our field point. And we're going to take our source point as a little volume element, and the charge there will be, of course, be rho at r prime times d tau prime. Don't forget the difference vector, which would be pointing from the dq to the field point. So obviously we're going to relate the potential due to this dq by giving this distance right here. The charge contained in this little volume element, we'll call it dq, r prime is equal to rho of r prime d tau prime. So going back to the way we talked about a point charge, we can consider that little dq as a point charge, and so therefore the differential of potential due to that point charge would be k times the magnitude of that charge divided by the scalar distance between the 2 points, and that's what this is right here. Putting in our dq, we have k rho of r prime d tau prime divided by the distance. And so all we're doing is we're generalizing this equation here where q is replaced by our dq. So if we integrate this over the volume, that will give us the potential. This is the integral of this distribution here over the volume, and so it's better represented here, k rho of r prime d tau prime divided by that distance. Well, you can extend this to other charge distributions, and this is really just like we did for the electric field integrals. So you can replace rho with a sigma or with a lambda, and of course the elements that you're interested in is a surface element or a distance element. Just repeating then, this is our volume density rho, so this is V from that. If we take a surface, then this is V sub r for charge on a surface. And then finally, if we do a line charge, then this is the potential due to that line charge where you're integrating over wherever this line charge exists. So let me just give you an example. If you had a curve like this and you integrated over this curve, and I think to be clear I should change this to a C prime. And then here's our k, lambda, defined on curve C prime. And then this is the distance between points on this line, which are at r prime, and the field point. So here's the field point up here. Here's the origin. And then our r primes, so this is our r primes wiggle, wiggle, wiggle around this curve. And we go around the entire curve to get the potential at this point by taking this distance here from every little part of the curve, which is the charge on that little element is lambda dl prime. Well, let's take a linear charge density, and so what we're going to do is form a ring of charge, and lambda is going to be constant along that ring. And what we want to do is find the potential at a point that's on the symmetry axis, which is the z-axis here. And so we have the possibility then of plugging directly into the general equation if we identify the vectors correctly. The first thing is the field point, and that's we call r, and that's just equal to z hat. So in other words, this red vector right here is r, and that's z hat, takes us to the point z. The r prime vector is any vector that points to the ring, so we'll take this one right here, and it's defined in terms of capital R, which is the distance, the length, and the angle phi. Let's consider then the unit vector that points along r prime, the cylindrical coordinate s, so that this would be s hat. So the length of r prime is capital R, and the direction is given by s hat. Now notice what we're going to do. We've got a little dq here, which is a length element, r d phi. So if we multiply that by lambda, that'll give us a dq. But we're going to take that little element and we're going to integrate by going around the circle. So we want to have phi into our equation. Well, where do we get it? Just like we did before when we did the electric field, you use the fact that you can represent the unit vector s in terms of x hat and y hat in Cartesian coordinates with the components cosine phi, sine phi. So when you do that, then you'll see that we'll get some phi dependence in our answer. First, take the two vectors and subtract them. So here's r minus r prime, and that's this vector here. You go from the dq to the field point. So this is the source point. That's along r minus r prime. Here's r right here. Here's r prime. But notice that this is slanted in this direction, which is actually taking minus r prime. And so when you add those two together, you get this vector here. So here's the difference. It's z hat minus capital R s hat. Rewrite the equation by putting in s hat. So here's the same z hat. Here's r times s hat right here. This is s hat. But what we need for the potential is the absolute value, the length of that vector. So to do that, you take the sum of the squares of the components. So here's the z component squared, here's the x component squared times r squared to get you the right length. And the same goes for sine squared here. So this is the y component squared. Notice that you get cosine squared plus sine squared, which is equal to 1. When you simplify, you get r squared plus z squared to the 1/2 power. And just remind you, dq is the charge density times the length of this little element here, and that's r d phi. Okay, so now we're ready to construct our integral. So here's the integral around the circle. Thing to notice is that the only variable that is being integrated over is our d phi. R is a constant, z is a constant, and everything else a constant. So you plug in your lambda, which is a constant, you plug in our r minus r prime, which is right here, and then you integrate. Well, all that does is gives you this thing right here, which is 2 pi. Bringing all that together, then here's your answer. This is the answer. You might want to rearrange it, but it's 2 pi r k lambda divided by the square root of r squared plus z squared. Well, notice that this quantity right here is the distance around the ring times lambda, which is just the q, total q that's on the ring. So if you want to, you can represent it by this. Pretty simple, and it falls off with z as you would expect. Actually has a value at the center, because if you let z equal 0, you have a finite value down here, which is r, by the way. So suppose you let z be much larger than r. It's real simple. You just let this be much larger than r, so throw away this. You have z squared to the 1/2 power, which is z. So you end up with k q ring divided by z. Well, remember, that's just the potential of a point charge. So if you get far enough away, this ring looks like it was just a point charge right at the origin. Well, what about a disk of charge? This should be a disk of charge. Again, along the symmetry axis, and it's going to have a constant surface charge density sigma. We're going to start with the fundamental equation for the potential of a surface charge, and so that's right here. S prime is the surface of the disk. To find a dq, we take a pair of rings, ds, apart. So this distance here is going to be our ds. And since we want to use primes, let's call this prime. So this would be s prime, and this would be ds prime here. So s prime would be the distance out. We'll take a differential in the phi direction. So this distance here would be s prime d phi. So let me go over that again. This set of rings here is what we're going to integrate over by just changing s prime. The inner one we'll call s, and the outer one is s plus ds and put primes on those. The area of this little element right here is going to be ds prime, that's this distance here, times this distance, which is s prime d phi. So that defines this area here. So if we multiply by sigma, which is the charge density, which is uniform, that'll give us our dq. All of this is the same. I haven't changed any of this from the previous problem. The only difference between the previous problem and this one is that instead of an r, we have an s prime. Because this is going to vary. We're going to integrate over s prime from 0 out to capital R. But other than that, the equation for s prime will be very similar. We do the same thing as we did before, find the length, and so now we have a length that depends on s, gives this equation here. We use the fact that this is equal to 1, and so we end up with this as our difference, and that's this right here. The length of this line for a given s prime is equal to this term here. So notice that if you started with 0, you would just have z. That would be the length, z squared to the 1/2 power. If you go all the way out to r, then this would be r squared plus z squared to the 1/2. So this is a variable, and that's what we'll have to integrate over, including phi. So here's the general expression. We substitute in a constant sigma, so that's this right here. We put in our ds prime, which is s prime ds prime d phi, and then we've already found the distance r minus r prime, which is this distance here. Regrouping, we can bring out all the constants, and we have an integral of s prime over s prime squared plus z squared to the 1/2 power ds prime. So that's either in the tables or use Mathematica. And so here's our prefactor, this one right here, and this is the answer. That you have the difference between r squared plus z squared to the 1/2 power and z. I've integrated this such that z is greater than 0. If you want to generalize it, it'll turn out that you can just take the absolute value of z, and that'll hold for both above and below the disk. I suggest you plot it. It's a little more complicated if you want to look at far distances away. So you take the answer that I have here, factor out a z, you'll get a term like this, minus 1. This is going to get small, so you can expand it, and so you'll get this quantity here, the first two terms, at minus 1. So then you cancel 1, and so you end up with this expression here. This is r squared over 2z because you have a z multiplying 1 over z squared. So you get 1 over z. Well, the same thing, if you regroup this, the 2's cancel, so you end up with pi r squared times sigma, and that's the q. This would be the q on the disk. Lo and behold, it looks just like we've obtained before, that it's the potential of a point charge. If you go far enough away, this disk looks closer and closer to a point. So those are just two examples. Next time we'll try to do a few more examples of finding the electrostatic potential.